Welcome back. In the previous lecture, we learned about general 2-qubit states. In this lecture, we consider a particular 2-qubit state for which the correlations violate Bell's inequality. Having talked about 2-qubit states in general, let's go back to the singlet state where we have this particularly compact way of writing it as the Pauli operators for the 2 qubits, sigma 1 and sigma 2. And we will now consider a situation where a state of this kind is emitted by a source. Qubit 1 travels over to the left to Alice's measurement device, and qubit 2 travels over to Bob's measurement device. So Alice can make a measurement at qubit 1 and Bob can make a measurement at qubit 2. And they make measurements that are specified by unit vectors A and B, such that the probability operator for Alice's two outcomes are half of 1 plus minus A dot sigma. So that refers to Alice's qubit. And for Bob, we have a measurement which has the probabilities operator of half 1 plus minus B dot sigma, where this is the sigma for Bob's qubit. And the A and the B are unit vectors. So, but now this is a measurement on both qubits of the 2-qubit system. So the probability operator for the two measurements together, they would be obtained as the tensor product of these two. Now, we have already agreed that we won't write tensor products, we will just label the two sigmas by 1 and 2. So we would then have a quarter of 1 plus or minus A dot sigma 1 and 1 plus minus B dot sigma 2, where the plus minus here is for the two outcomes for Alice, and this plus minus is for the two outcomes for Bob. And so this probability operator has two of them with plus minus for Alice and another two of them with plus minus for Bob. So altogether we have 4 of those probabilities operators. So let me just label them with two plus and minuses. So there's a plus plus probability operator where there's a plus sign here, plus sign there. There's a minus plus or probability operator with a minus sign here and a plus sign here, and so forth. So if I'm now looking at the probability for getting plus result here, plus result there, probability of a minus result there, plus result there, and so forth, it will be the expectation value of this probability operator. So the probability for Alice getting plus or minus and Bob getting plus and minus, so just to be clear, this refers to Alice, which is qubit 1, and this refers to Bob, so this is for qubit 2. So that's the expectation value of this operator with this state, and that's just going to be a quarter of 1. And now where we have the sigma 1, we will get the plus or minus A. So there's a minus, and then it's plus minus A, depending on Alice's outcome, dotted into, and then where we have sigma 2, we'll get plus minus B. And so this plus minus is for Alice, and this plus minus is for Bob again. So they correspond this plus minus, and this pair of plus minuses, this pair of plus minus. So altogether we have these 4 combinations, but there are only 2 different probabilities. Namely, if I have the same sign and different signs. So we have a quarter of 1 minus A dot B for the same sign, and a quarter of 1 plus A dot B for the opposite sign. And since A and B are unit vectors, A dot B is the cosine of the angle between the two unit vectors, and so all of these numbers are clearly numbers between 0 and 1. And since we have 4 of these probabilities, we have 2 probabilities of this kind and 2 probabilities of this kind. When we add them up, we get a quarter and a quarter plus a quarter and a quarter, so that's 1. and the AB terms, two of them will come with a minus sign, two of them will come with a plus sign, so the sum of these terms is just 0. I summarized these 4 probabilities in this table. So Alice gets outcome +1 or -1, Bob gets outcome +1 and -1. When the two outcomes are the same, the probability is a quarter of 1 minus A dot B. If the outcomes are different, the probabilities are 1 plus A dot B. And if I sum up the two kinds of outcomes that Alice can get when Bob gets +1, well, the sum of those is a half. The two outcomes for Alice together have a probability of a half when Bob has -1, which is just to say that the probability for Bob to observe the +1 outcome, that's a half, and Bob gets the outcome -1 also with a probability of 1/2. And also for Alice, we have the individual probabilities of 1/2 and 1/2 for the measurement outcomes +1 and -1. So now let's imagine that we ask Alice to make a prediction about the outcome that Bob will observe for the next qubit that reaches him from the source. And so Alice will just say, well, I mean, Bob has these probabilities of a half for outcome +1 and a half for outcome -1. So she predicts that he will measure both outcomes with equal probability 1/2. And that means that Alice would describe Bob's qubit 2. So this is Alice describes Bob's qubit, which is number 2, by a statistical operator for the second qubit, which is just a half times the identity for the second qubit. So no preference for +1 and -1. But now Alice measures her qubit and she finds the outcome, say, +1. And if she is now asked, what are the probabilities that Bob will get +1 and -1? Well, then she will say, well, in this case, Bob's probabilities are half of 1 minus A dot B and half of 1 plus A dot B. Because my probability is a half, so half of the time these occur. So this is, I have to normalize by this 1/2. And so after observing outcome +1, Alice's statistical operator for Bob's qubit is row 2, and this is for outcome +1, and that will be half of 1 minus A dot sigma 2, such that Bob, then getting outcome +1, he will get 1 minus A dot B, and getting outcome -1, the sigma 2 will be replaced by minus B, and the calculated probability is a half of 1 plus A dot B, exactly as this table tells you. And of course, in those cases where Alice measures her qubit and gets the outcome -1, then in that case, she will use these values in the table, and her statistical operator for Bob's qubit will be the one which has the plus sign here. So we have this situation that Alice's description of Bob's qubit before she measures her qubit or before she knows the outcome of the measurement of her qubit is just that of the completely mixed state for Bob's qubit. But once she is aware of the outcome of the measurement on her qubit, she will update her predictions about Bob's qubit in accordance with what she found out about her qubit, because she knows that the two qubits are linked in this entangled state that is emitted by the source. So this update of Alice's prediction when she has additional information, here she doesn't know anything about the measurement outcome on her qubit. Here she knows the outcome of the measurement on her qubit. So these are two different states of information for Alice, and accordingly she will have different probabilistic prediction for Bob. So this transition from here to here, which just takes into account additional information, this procedure is what we call state reduction. It is not something that is really particular to quantum mechanics. It's a feature of all statistical theories. Whenever you have uh, a formalism that allows you to make statistical statements about future events, you will have state reduction because your predictions will change as soon as you have additional information about the situation. Just think about the weather report. So you want to know whether it will rain tomorrow night for booking an outside table at the dinner restaurant. And today's weather report may say, well, there is a 20% chance of rain tomorrow. But by tomorrow afternoon, the sky may be full of black clouds and you now expect rain with 90% probability or higher, just because you now see that the situation is really different from what you knew yesterday. So additional information will always have a bearing on statistical predictions for future events. You get additional information, you will have to revise your predictions, you will have to update your description of the system and calculate the probabilities accordingly. So this is what Alice does here. So first she just knows that the source emits the qubit pair in this singlet state, and so asked what is the probability that Bob will find +1 and -1. Well, she says, well, there's an equal chance for +1 and -1. But later she knows that her measurement returned the value +1, and in which case she will say, oh, the probability for Bob getting +1 is now no longer a half, it's a half minus a half of A dot B. And the probability for getting -1 is a half of 1 plus A dot B. That is nothing mysterious. Alice measures here and goes through this transition from this row 2 to this row 2. This is just something that is happening in Alice's mind or on her piece of paper, where she says, oh, now I have to recalculate what are the probabilities for Bob. It is not a spooky action at a distance between Alice's measuring apparatus and the qubit on the way to Bob's measuring apparatus. No such action at a distance is happening. All that is happening is Alice updating her predictions about Bob's measurements in the face of additional information. Let's take another look at this table and consider a couple of situations. So first let me consider the situation that the directions chosen by Alice and Bob are perpendicular. So the dot product of the two unit vectors A and B is 0. And if we have that, then this table, where we have the Alice's outcome over here and the Bob outcomes over here, well, the table will just have entries of 1/4, 1/4, 1/4, 1/4. So whatever Alice observes and what Bob observes is completely uncorrelated with the other person's measurements. So in this situation, there are no correlations whatsoever. Alice's measurements and Bob's measurements are completely independent, statistically independent. So the second case is when A and B are the same. So Alice and Bob are measuring in the same direction. And then A dot B is just equal to 1. And this table will now have other entries, namely 0 for the same outcomes and half for the opposite outcomes. So whenever Alice gets the plus outcome, Bob will necessarily observe the minus outcome. When Alice observes the minus outcome, then Bob can only observe the plus outcome. So these measurement results are very strongly correlated. And one speaks of negative correlations because it's the opposite results that are correlated with each other. So this would be a situation of negative correlation. Now let's compare this with A being negative B, and then this dot product is -1. And if that's the case, then we have a different table, namely with the negative B, a -1 here, we have half here, we have 0 there, we have 0 here, and we have half there. So now, whenever Alice finds the outcome +1, Bob cannot find outcome -1, he also will find outcome +1. And when Alice finds outcome -1, Bob will also find outcome -1. So again, we have very strong correlations. In this case, we have very strong positive correlations. So we have the negative correlation when A and B are the same, and we have the negative correlation when A and B are negatives of each other. So finally, let's look at the Bell scenario, which is really a situation like this. So Alice makes a measurement, Bob makes a measurement, and they choose different A's and different B's. And then we calculate what is called the correlation function. And in this context, it just means that we add up the probabilities for the positively correlated detection events. So that's the probability of Alice getting plus and also Bob getting plus the probability for both getting the -1 outcome. And we subtract the probabilities for the anti-correlated event. So Alice can get plus and Bob gets minus, or Alice gets minus and Bob gets plus. And so in this table, it means that we add the two diagonal entries and we subtract from that the sum of the two anti-diagonal entries. So after we are done with this little calculation, we find minus A dot B for this correlator. Now, in the Bell scenario, Alice has two measurements, A1 and A2, and Bob has two measurements, B1 and B2, and we have the correlation function that we measure for the settings A1, B1. We measure also the correlation function for the settings A1 and B2, and we measure the correlation functions for the settings A2 and B1, and we measure the correlation function for the setting A2 and B2. So 4 of those correlation functions in total. We add up 3, we subtract 1. It doesn't really matter where we put the minus sign, but let's just put it on the A2, B2 term. So this is negative A1 dot B1. This is negative A1 dot B2. And this is negative A2 B1. And this, with the minus sign, is positive A2 B1. So going with B1, we have negative A1 plus A2 dot B1. And going with B2, we have negative A1 minus A2 dot B2. So that's just putting all of these pieces together. And now we think of how to choose the various vectors and begin with choosing B1 and B2 such that this is particularly large. So we maximize over the choices for B1 and B2. And that's quite simple, because all we have to do is choose the unit vector B1 in the direction of negative A1 plus A2. And we choose the unit vector B2 in the direction of negative A1 minus A2. In which case, this term will just be the length of A1 plus A2. And this term will be the length of A1 minus A2. Now, what are these lengths? Well, if I write them out as the the square root of the squares of these sums and difference vectors, then the first one is 2 plus 2 times a1 dot a2, and the second one is square root 2 minus 2 times a1 dot a2. Because here when we square we get a1 dot a2, and here when we square we get negative a1 dot a2 with a factor of 2, and this 2 comes about from squaring a1 and squaring a2, which are both unit vectors. Right. So at this point we have to decide how do we choose a1 and a2. And if we choose them parallel or orthogonal, this is not going to be extremely helpful. So let's just be open-minded about the direction of a1 and a2 and recognize that the only thing that matters is this dot product of a1 and a2. So for the dot product of a1 and a2, let me just say that that's the cosine of the angle between a1 and a2, and this angle I will call 2 phi. So the phi itself is an angle between 0 and maybe 90 degrees, which is pi half. And so what we have here is 2 plus 2 times the cosine, and that is, with the square root, is 2 times the cosine of half the angle, which is phi. And here we have 2 minus 2 times the cosine of 2 phi. That gives us 2 times the sine of phi. And I don't have to worry about absolute values of cosine and sine phi as I take the square root, because with this restriction on phi, this cosine and the sine phi are both positive. And now rewriting this in a slightly different way as the square root of 8, and then the cosine of phi times the cosine of pi quarter plus the sine of phi times the sine of pi quarter, where we just remember that the cosine of pi quarter, the cosine of 45 degrees, and the sine of pi quarter, the sine of 45 degrees, both are 1 divided by the square root of 2. So taking the square root of 8 divided by the square root of 2 is the square root of 4, which is the factor of 2 that we have in common. And this combination of trigonometric functions is just the cosine of phi minus pi quarter. And now the cosine can be as big as 1, and so we now choose the cosine such that the cosine of, we choose the phi such that the cosine of phi minus pi quarter is exactly equal to 1, and so then we get square root of 8. And so this comes about because we optimize the angle of phi. So it tells us which angle to choose between a1 and a2, such that this expression is largest, and then with a particular choice that we make for a1 and a2 with this angle, we then know what to choose for b1 and b2, namely in the direction of negative a1 plus a2 and in the direction of negative a1 minus a2. And so what we then find is that this combination of correlations for 2 settings for Alice and 2 settings for Bob, 3 of them added, 1 of them subtracted, the number that we get is the square root of 8. The largest number that we can get is square root of 8 if we have the singlet state emitted by the source, and Bob and Alice do these measurements on their qubits. And we remember from the first cycle of these lectures, actually the very first lecture in the first cycle, is that if there is a hidden deterministic mechanism that decides the outcomes of Alice and Bob's measurements in advance, then the largest number that we can get is 2 for this correlation functions. But for the quantum experiment that we can easily conduct, and such experiments of course have been conducted frequently by now, we can get a number which is significantly larger than 2, namely the square root of 8, which is about 2.8. In summary, the correlations that result from the 2-qubit singlet state are stronger than allowed by Bell's inequality. In the next lecture, we talk about maximally entangled states, for which the singlet is an example, and see that systems in a pure state cannot be entangled with another system.